AI video is starting to move from generate frames to something much more controlled, editable scenes, preserved subjects, and geometry that actually holds together. The big shift is that these systems are no longer guessing everything from scratch. They're using structure, tracks, and layered composition to keep motion, identity, and 3D consistency intact. That matters because it pushes video AI closer to real production workflows, where precision beats raw realism. Keep watching, because the interesting part is how these models are learning control without sacrificing generation quality. Let's explore the first paper. Flat feed-forward latent triangle splatting for geometrically accurate scene generation. FLAT, developed by Google Research with Oxford VGG and TU Munich affiliations, is a feed-forward image to 3D scene generator that decodes explicit triangle splats directly from frozen video diffusion latents in a single pass instead of regressing volumetric 3D Gaussians. The key novelty is array-centered triangle parameterization. Each token predicts depth, a constrained Cholesky-style 2D shape transform, and residual local rotations, which prevents degenerate triangles and stabilizes training. FLAT also replaces the standard triangle splatting window with a product-based soft coverage function that extends support beyond boundaries and improves gradient flow. Trained on Real Estate 10K and DL3DV with real and synthetic videos, using Uni 3C, built on WAN 2, WAN and supervised by photometric, LPIPs, depth, and normal losses, FLAT's triangle variant reaches a mean normal cosine of 0.853 versus 0.587 for 2DGS, while preserving competitive appearance. On Real Estate 10K, it reports 21.45 PSNR, 0.71 SSIM, and 0.245 LPIPs. With the optional 250 step refinement, it rises to 23.01 PSNR and 0.79 SSIM. For game engine compatibility, FLAT converts its triangle soup into an opaque mesh. The resulting meshes use 0.5 M vertices and achieve 21.23 PSNR on Real Estate 10K, outperforming 3DGS mesh extraction by more than 7 decibels. The paper also provides a systematic comparison of 3DGS, 2DGS, and triangles under identical latent decoding conditions, showing that triangles trade a small amount of PSNR for substantially sharper, more physically grounded geometry. Let's explore the second paper. Go with the track video compositing and motion control with point tracking. Go with the track, from Netflix, Eyeline Labs, and the University of Oxford. Unifies reference image compositing and motion control in a single video diffusion transformer by conditioning on multiple reference images plus reference-anchored point tracks. The core idea is a spatially aware point track embedding. Each trajectory is encoded from its full coordinate sequence with a coordinate-wise MLP and temporal max pooling. So embedding similarity reflects spatial proximity instead of using random IDs. A lightweight adapter then maps up to 15,000 pixel space tracks into WAN 2, 1/2, 2's 4 times, 16 times, 16 patchified latent space without the motion detail loss caused by naive subsampling. Training mixes real video, static scene, and synthetic data, including approximately 500K curated videos and a 3:7 synthetic to real ratio, with 4:9 frame clips at 480 times 832 and up to 24K iterations. On Davis 2017 and TapVid 3D, ADT, the method consistently beats baselines such as Diffusion as Shader, Go with the Flow, Tora, ATI, and WANMove. For example, on Davis Dense Tracks, it reaches FID 28, FED 322.8, and EPE 7.709, while on TapVid 3D, ADT Dense Tracks, it reaches FID 41, FED 314.3, and EPE 4.429. In a 4-5 participant user study, it wins 46.2% for motion following, 43.5% for subject preservation, and 44.3% overall quality, and it enables mesh compositing, key point-driven subject transfer, and camera retargeting for both static and dynamic scenes. Let's explore the third paper, Vera, a layered diffusion model for content-preserving video editing. Vera, developed by California Institute of Technology and Netflix Inc., is a layered diffusion framework for content-preserving video editing that avoids regenerating the full frame. Instead, it jointly predicts an edit layer, an alpha matte, and a natural composite video, then uses a mixture of transformers design with 3 separate DITs and joint self-attention so the edit branch can stay creative while the preserved content is retained by construction. The method is trained with flow matching on a curated layered dataset of 486 keyframes at 832 times 480, built from synthetic composites and realistic single and multi-object videos with accurate alpha mats and effects such as shadows and reflections. On 72 object addition tests and 69 background change tests, Vera 1.3b reaches 25.3 decibels PSNR for object addition and 35.2 decibels for background change, while Vera 1.4b reaches 26.1 decibels and 36.2 decibels, respectively. It also tops instruction compliance on object addition with 4.13 IS and remains competitive on edit quality. The paper's ablations show that the layered formulation, the composite branch, and multi-joint attention are all necessary, and a human 2 AFC study over 513 valid trials preferred Vera on content, preservation, and instruction compliance. That's a wrap on today's AI paper highlights. Thanks for watching.